Hello everyone, welcome to 10th week of the discussion session of the course Strength of Material course offered by NPTEL. The course instructor of this course is Professor Shriman Kumar Bhattacharya. He is a professor from IIT Kharagpur. Myself Asif Raza, I am your teaching assistant. I am a PhD scholar from Department of Civil Engineering, ISC Bangalore. Since it's the 10th week, we'll be discussing questions relevant to assignment number 10, and as you all know that the due date is still not over, so will not be discussing the exact question of assignment. Rather, we'll be discussing questions similar to the assignment which will help you in solving the questions. So we'll start, and I'll ask all of you to use the discussion forum as much as possible. If you have any doubt, you can post it there. Okay, so we'll start. Uh, Before going into solving questions, I'll just start with the basics. What is needed in this assignment? What is needed in this discussion session? Most of all. So let's do this. Okay. So first thing, you have come across with bending stresses, shear stresses, and you have been solving it independently. The questions were kind of only questions depending on bending moment and the stresses pertaining to it, and uh, stresses pertaining to the torque or twisting moment. Now we'll see the cases where when both the cases are acting simultaneously in a system, what kind of stresses will be generated. So yeah, so the topic covered in this week is combined stresses. Okay, so we just need to see whatever we have learned. Like, if you remember, there was a flexural formula. Flexural formula. It was given by this. I'll just write it here as a sigma b for bending. Now for this, I'll just use this to relation and write as sigma b is equal to, okay, this is the first one. Now the torsion formula. I hope you guys all remember what are the notations, what do they mean. Okay, so this is, so again I'll use this first two relation and write T on IP times R. Okay. This is the bending stresses generated, and this is the shear stresses generated due to the torsion. Now, if it is acting simultaneously in a system, so if you remember the equivalent stresses, to find the equivalent normal stresses and shear stresses, if we are given with stresses in a element, we were able to find what would be the maximum and minimum stresses generated in a system. That was given by the principal stresses So sigma 1 comma 2, if you remember, it was given by this relation. And max was given like this. Okay, now let us use this to find this maximum, find the principal stresses and maximum shear stresses generated due to the combined system. So for first thing, shear stress, principal stresses, and that is like sigma x. I'll just write it as okay. One more thing is let us take the case of circular case. So for circular shaft, is pi d4 by 32. This thing to be kept in mind. Y would be d by 2 and R also d by 2. Substituting it, sigma by 2. First thing, I'll just write sigma b, it comes out to be m by y m by 34 by 64 d by 2. This will be 32 m by pi dq. Would be t by d4 by 32 t by 2, that would be 16t by dq. Now substitute that in this. This will be 16 m by pi dq plus minus 16 m by pi dq whole square. So if you see this is actually, if I write this in terms of I, it is 32 m equivalent by pi dq. where m equivalent is half of m plus minus m square plus t square. I'll write this properly. Sigma 1 comma 2 is 32 m equivalent by d cube, where m equivalent is m plus minus m square plus t square. So equivalent bending moment is kind of the maximum principal stresses generated due to the combined system. The principal stresses generated due to the combined system, the same effect will be produced if we are giving the bending moment value to be equal to this. Okay. Similarly, we can find tau max, and that would be tau max is root 16 m by pi d cube whole square plus 16 t by d cube whole square. So I can take this out, 16 by pi d cube root m square plus t square, and I can write this as 16 t equivalent by pi d cube, where t equivalent is equal to root m square plus t square. So this is kind of the maximum shear stress produced due to the twisting, like combined effect of bending moment and twisting moment in this system would be same if we apply only the twisting moment value with the value equal to this. Okay, so these two things need to be kept in mind, the equivalent bending moment and equivalent torque. Okay, so this is just what we'll be doing in this session. Okay, let's start it. Let's start doing today's session. So first question is, I'll just notify it. The question is, a circular shaft is subjected to a bending moment of 400 Newton meter and twisting moment of 300 Newton meter. The equivalent bending moment for which the shaft should be designed is. So the question is for the circular shaft itself, and we need to find equivalent bending moment. So what we have just discussed right now, we'll be using this formula, and yeah, this is to be kept in mind that we solve this keeping in mind that this is a circular shaft. If there is a different geometry involved, we'll have to work around this complete thing. Okay, yeah, so let's do this. So we are given with the bending moment value equal to 400 Newton meter. Okay, and twisting moment value equal to 300 Newton meter. We need to find what is equivalent bending moment. So let's find it, and that is given by half m plus minus m square plus t square. Okay, and this would be equal to half m would be 400 plus minus m square is 400 square plus 300 square. This would be equal to half 400 plus minus 10. This would be 500. The values will come out to be 400 plus 5, 900. So 450 comma minus 100, so 50. So out of this all, ME would be equal to 450 Newton meter. So answer would be option C, 450 Newton meter. Okay, let's also solve what will be my equivalent twisting moment. For this case, it would be equal to root m square plus t square, and that is so the A is root m square plus t square, and m is 400 and t is 300, and if you solve this will come out to be 500 Newton meter. Okay, so this is quite a straightforward question. I hope nobody will have doubt in this question. Moving on to the next question. The second question is, a circular shaft is subjected to a bending moment of 200 kN meter and a torque of 600 kN meter. If the allowable stress in bending is 80 megapascal, the minimum diameter required is, and the options are 321 mm, 413 mm, 335.7 millimeter, or 375.6 millimeter. So, in this question, again there is a combined system of the application of the bending moment as well as the torque, and the system is it says that system maximum bending stress it allows it 80 megapascal. So to solve this question, we'll find the equivalent bending moment and then find the maximum principal stresses. Through that we'll be able, like, since we'll keep that as the design stress as 80 megapascal, and using that we'll be able to find the diameter for this system. Okay, so let's do this. So we are given with circular shaft. Okay, bending moment as 200 kilonewton meter. Since this won't be a direct case, we'll have to solve it further. So I'll convert everything into Newton and millimeter in those equivalent units. So with that it will be equal to 200 into 10 to the power 6 Newton millimeter. Newton millimeter. Okay. Similarly, torque is given as 600 kilonewton meter. It will be equal to 600 into 10 to the power 6 Newton millimeter. Allowable stress in bending, I'll just write sigma max is 80 megapascal, that is 80 into 80 Newton per square. Yeah, to solve this we need to first find ME, that is half of m plus, I'll just take the plus case, m square plus t square, and this is it, So half m, this I'll just take 200 square and 600 square, and I'll just multiply it 10 plus 6 outside. So let's solve this. Move to 200 plus 600. So this comes out to be 416.23 into 10 power 6 Newton millimeter. Okay. Now the next step would be take the case sigma max, and that is 32 ME by pi d cube, and we'll just equate it. It is given as 80, 32 equivalent is 416.23 into 10 power 6 upon pi d cube, and the stresses generated due to this equivalent bending moment, it should be less than this design stress. Okay, so I'll just this will be greater than equal to 32 into 416.23 into 10 power 6 upon pi times 80, and this is equal to is equal to 52.99 into 10 power 6. This would be equal to this T is greater than equal to 375.62 mm. Thus our D minimum diameter would be equal to 375.6 mm. Let's see and see the options. Yeah, so correct answer is option D, 375.6 mm. Okay, I hope this is okay for all. Okay, yeah, moving on to the next question now. Yeah, the third question is, in a circular shaft the applied moment is 1.3 times the applied torque. The ratio of the maximum shear stress to maximum principal stress is, and the options are 0.4, 0.45, 0.56, 0.2. So yeah, so first thing first, it's a circular shaft, so it's okay to use the earlier formula, and the question is given as the applied moment and it's equal to 1.3 times of applied torque. Okay, we need to find the ratio of tau max upon sigma. 1. Okay, what would be this? This is the question. Okay, so let's solve this. First thing first, we need to find equivalent bending moment and equivalent torque. Equivalent bending moment is equal to half of m plus m square plus t square, and this is equal to 1.3 t plus 1.3 t square plus t square, and this is equal to 1.3 so this comes out to be 1.47 t. Okay, 1.47 t. M equivalent is a kind of it's a 1.47 t. Now next thing is equivalent torque, that is equal to 1 m square plus t square, and that is equal to 1.3 t whole square plus t square. This is equal to 1.3. This is equal to 1.64. Okay. Now next part is we need to find the maximum stresses pertaining to the equivalent bending moment and the equivalent torque. So through the equivalent bending moment would be able to find the maximum principal stress, and that would be equal to 32 ME by dq, and tau max would be equal to 16 TE by pi dq. Okay, now if you want to find the ratio of these two, that is tau max upon sigma 1, that would be equal to tau max will come out to be, let's write it, 16 TE by dq divided by 32 m by pi dq, and this will be equal to TE upon 2m. Now this substitute what we have the values. For T it's 1.64, right? Yeah, and 2 times of bending moment is 1.47 T. Let's find this. So 1.64 divided by 2 and divide by 1.47, and this comes around 0.5578. So roughly we can say it's equal to 0.56. Thus if we see those options, the correct answer would be option C, 0.56. Okay, so it's just a step further what we have been doing. In the first question we just went till finding the equivalent bending moment and equivalent twisting moment, and then further step we found the maximum stresses and and using that we'll be able to find the minimum diameter. In these cases, we find the equivalent bending moment, we find the stresses pertaining to the bending moment and the twisting moment, and then we just need to take the ratio of it to find the ratio as asked in the question. Yeah, so okay, I hope this is clear for all. If you guys have any doubt, you can post it in the discussion forum if needed. I'll try to answer if possible, or else I'll just try to give the answer in the next session also. Okay, moving on to the next question. Next question is, a circular shaft of outer and inner diameter are 200 mm and 100 mm respectively. It is subjected to combined action of axial load P equal to 750 kN, bending moment equal to bending moment value is 45 kN and twisting moment is 62 kN. The maximum principal stresses and maximum shear stresses generated in the system is, and the options are 92.5 megapascal and 42.1 megapascal respectively, 61.12 megapascal, 62.71 megapascal respectively. Option C is 109.2 megapascal, 62.71 megapascal respectively, and option D is 42.1 megapascal and 62.71 megapascal respectively. So first thing is, it's a circular shaft question, so we can use the formula as given. Now okay, so it's not a solid shaft, it's a hollow shaft, but one thing can be made clear about this is, in this thing also, the I is equal to pi d4 by 64, and that is if I write it, TO4 TI4 64 and IP is so this is a similar thing. Okay, so to solve this question, we'll be doing step by step. Okay, okay, let's first thing first, we should write what is given in the question. The outer diameter is 200 mm, inner diameter is 100 mm, combined action axial load P is 750 kilonewton. I'll write it as 750 into 10 to the power 3 Newton. Bending moment value is 45 kilonewton meter. That would be 45 into 10 to the power 6 Newton mm. Twisting moment value is given as 62 kilonewton meter. Write 62 into 10 power 6 Newton mm. Okay. Yeah. So first thing, what would be the area of the system? This would be equal to pi by 4 d square minus di square. This would be equal to pi by 4 200 square minus 100 square, and this comes out to be This comes out to be 223,561.94 mm square. Okay. Let's find I and IP as well. So I pi by 200 to the power 4 100 to the power 4, right? Yeah. So this 2 pi 64, and this comes out to be 73631 077.82 mm to the power 4. IP would be pi by 32, same thing, right? But just double of this, and so twice of this will come out to be 147,262,155.64 mm to the power 4. Okay. Most of the things done. Now we need to find maximum principal stresses and maximum shear stresses. Okay, so first let's find maximum shear stress. Okay, so in this case, in the given question, there is a bending moment as well as there is a direct stress. So we have to combine this thing to uh, 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 okay, to get the bending stresses due to these two systems. Then we'll try to find the equivalent uh, system stresses due to the equivalent system. Mm, uh, okay, first we need to find direct stress. It's equal to, just write as sigma a, it's P by A, and the value would be 750 into 10 power 3 upon 23561.94. It will come out around 750 divided by 23561.94. This is 31.83 megapascal. Now bending stresses due to bending stress due to bending moment, and that would be m by I d naught by 2, and that would be 45 into 10 power 6 upon 73631,077.2 d naught by 2, that would be 100, but let's write it as complete thing. 45 divided by 73631,077.2. 200. This comes around 61.11, or rather 61.82, no, 12 megapascal. Now shear stress also. The shear stress tau is that is T I P same D naught by 2, that is tau would be equal to twisting moment value is 62 into 10 power 6 upon IP is 147 26215 262,155.64 into 200 by 2. This will come out to be 147 262 42.1 megapascal. Okay. Now we need to find what maximum principal stresses and maximum shear stresses. Okay. To find maximum shear stress, the max would be equal to this sigma A plus sigma B by 2 whole square plus tau square, and this would be equal to just write it 31.83 plus 61.12. Because the direct stresses and the bending stresses will give the those will combine to give as the normal stresses, right? So let's find this. 61.12 divided by 2 plus 42.12. This comes out to be 62.71 megapascal. The next, now maximum principal stress. For maximum principal stress, sigma 1, that would be equal to sigma A plus sigma B by 2 whole square plus plus minus, I'll just write this one as tau max. This is again 31.83, not the square this time, yeah, 31.83 61.12 by 2 plus minus 62.71, and it will come out to be 31.83 plus 1, 2, 109.2 185, comma, minus 16.235. Using all the options I saw earlier, it would be sigma 1 would be equal to 109.185 megapascal, or I can write it as 109.2 megapascal. This so our maximum principal stress value comes out to be 109.2 megapascal, and maximum shear is 62.71. Let's see all these options. So shear stress, okay, maximum principal stress matches with the only option of option C. Yeah, and 62.7 megapascal is there already. So yeah, correct answer is option C. Maximum principal stress is 109.2 megapascal and maximum shear stress is 62.71 megapascal respectively. Okay, so this was a lengthy question. It just needed the input of all the data provided and just direct calculations what we have been doing earlier. Okay, yeah. Moving on to the next question. Question number 5. A steel post of length 3 meter is subjected to a compressive axial load of 100 kN at an eccentricity of 50 mm from the center of the post. The cross section of the post is hollow with outer and inner diameter as 250 and 200 mm respectively. The maximum compressive stress is what? Options are 11.2, 7, 14 or 70. Okay, so this is also a circular shaft question. We're given with steel post of length. I'll just write length as 3 meter, 3000 mm, axial load of 100 kilonewton, 100 into 10 power 3 Newton, eccentricity E as 50 mm from the center of the post. The cross section of the post is hollow with outer diameter is 250 mm and inner diameter as 200 mm. Yeah, okay. This is a compressive load. So we need to find the maximum compressive stress. Yeah. Okay. Okay. So let's solve this. Maximum compressive stress. So first thing, what would be direct stress, or rather than writing direct, just write axial stress. That would be P upon A. Okay, before this I'll just find all the required values. A, it's equal to pi by 4 A naught square minus T. Okay, that is pi by 4, 200, 250 square minus 200 square. This comes out to be This comes out to be 17671.46 mm square. I would be required, yeah. I would be equal to pi by 64 d14 minus di. This would be equal to pi by 64 250 to the power 4 minus 200 to the power 4. Let's find it. 250 to the power 4 minus 200 to the power 4 into pi divided by 64. This is equal to 113,207,782.15 mm to the power 4. Now next thing is we'll find the axial stress. The axial stress is equal to P upon A, and that is 100 into 10 power 3 upon A is 17671.46, and this is equal to 17671. This comes out to be 5.659 megapascal. It's a compressive one. Bending stress, that would be equal to m by I y. In this case it would be d naught by 2. This I'll just substitute. So m is equal to p e I d naught by 2. P is 100, eccentricity is 50, I is 113,207,782.15 times this is 250 by 2. 100 into 50 into 250. Okay, 100 into 10 power 3 into 50. One 113,207,782.15, and this comes out to be 55.21 megapascal, both compressive and tensile. So I can find the maximum compressive stress. Stress, as there is no I'd say twisting moment, so this is it. So we'll just add this 2 and it would be equal to 5.651. 60.869 or 60.87 megapascal. Okay, so this doesn't match it. Did I made any mistake in the calculation? Let me see. 150 into 10 power 3 to 250 divided by 2 divided by 113207782.15. Okay, this is where I made a mistake. This is equal to 5.521 megapascal. Okay, so 5.659 plus 5.521. 5.659. This comes around 11.18 megapascal. Let's see the options. Okay, so out of all the options, this can be written as 11.2 megapascal, and consequently our right option would be option A, 11.2 megapascal. Okay. Moving on to the next question. Question number 6. A concrete column carries an axial load of 600 kN, a bending moment of 60 kN at its base. An isolated footing of size 2 meter by 3 meter with 3 meter side along the direction of the bending moment is provided under the column. Centers of gravity and foot of column and footing coincide. The net maximum and minimum pressures in kilonewton per meter fall under the footing respectively. Okay, so this is a scenario where it's not the circular shaft, it's a rectangular thing. So we need to solve it what we have been doing by the basics. Okay, first thing first, we should write what is given. So the axial load is 600 kilonewton. Bending moment 600 kilonewton. I can write it as 600 into 10 power 3 newton. Bending moment is 60 kilonewton meter. That is 60 into 10 power 6 newton millimeter. An isolated footing of size. Dimension is 2 millimeter by 2 meter by 3 meter. So I can write area of this is 2000 times 3000. That is 2 3 is 6 into 10 power 6 millimeter square. Okay. With 3 meters side along the direction of the bending moment. Now we need to find. So what will happen is there is a stresses due to this direct load or axial load. So with that axial stress would be generated, I'll just write it as sigma A, that would be equal to P by A, and that is 600 into 10 power 3 upon area is 6 into 10 power 6, and this is equal to this is equal to 10 power 5.1 megapascal. Okay, and bending stresses would be equal to m by I y. Now to find the maximum and minimum pressure, this will be kind of plus minus kind of thing, because at one of the side bending stresses generated would be tensile, and at the other side it will be compressive. So plus minus thing would be there, and bending moment value, like okay, so m, let's write bd cube by 12, and this has d by 2. The sigma b is plus minus m 6 bd square, and it's already given that uh, mm, that bending the direction of the bending moment is along the 3 meter side. So b is 2000 and d is 3000. Then I can substitute other thing is 60 into 10 power 3, b is 2000, d is 3000 square. This will give me uh, divide by 2000, and d cube by 12, bd square by 6, yeah. So this is okay. Yes, then okay, this is 10 power 6, 10 power 6, and solving this will get 0.02 megapascal. This are if I write sigma as sigma a plus sigma b, it will be equal to 0.12, and 0.1 minus 0.02 is 0.08. So if I write it in terms of kilonewton per meter square, it would be equal to 120 kilonewton per meter square and 80 kilonewton per meter square. Let's see the options. Yeah, so option number second matches with the findings of our calculations. Okay, moving on to the next question. Question number 7 is the maximum normal stress and the maximum shear stress analyzed for a shaft of 150 mm diameter under combined bending and torsion were found to be 120 meganewton per meter square and 80 meganewton per meter square respectively. the bending moment to which shaft subjected is. Yeah, so this is quite a good question. Uh, in this, we have to rather go inverse way. As of now, we have been solving. We have been provided with the torsion and bending moment and the dimensions of the system. This time, we need to find the stresses and uh, equivalent bend moment and whatnot. But this time, the stresses have been already provided. Dimension of the system is provided. We need to find the bending moment subjected to this system. Okay. So question is, it's given sigma max as 120 mega 120 mega Newton per meter square. I can write it as, if I convert it into Newton per mm square, then the down it would be 10 power 6, and the above it will be 10 power 6 Newton. So 120 Newton per mm square. And tau max is given as 80 mega Newton per meter square. That would be equal to 80 Newton per mm square. And the diameter of the shaft is given as 150 mm. We need to find what is the bending moment applied to this system. Okay, so to solve this question, if you collect sigma max, it's equal to what? 32 me by pi d cube. Yeah, and uh, tau max, it's equal to 16 Te by pi d cube, where me is half of m square plus t square, and Te is root m square plus t square. So let's use tau max first. Tau max is 16 Te by pi d cube. Te is tau max times 16 pi d cube by 16. This is equal to this is equal to tau max is 80 into pi d is 150 by 16. This is equal to 150 cube into pi to 80. This is equal to 53014376103. Okay, now me would be equal to sigma max to pi d cube by 32, and that is 120 to pi into 150. cube by 32. This is equal to divide by 39760,782.02. Now if you see, ME is half of M plus TE. So with this, M can be written as 2ME minus TA. We can find it 39760,782.02 minus or times 2 minus 53014 376.103. So this comes out to be 26507.188.01, and this would be in Newton millimeter. To convert it into kilonewton meter, it should be equal to 26.51 kilonewton meter. Let's see what is there in the options. Okay, yeah, so option D matches perfectly. 26.51 kilonewton meter is the bending moment applied in the system. We can find the torsion applied in the system also if we just use TE formula, as we already have TE and we already found M, so with this we can find the torsion applied in the system, so we can easily do that. Okay, moving on to the next question now. Question number 8 for today's session is, for the cantilever bracket PQRS loaded as shown in the figure, PQ is equal to RS equal to L and QR is equal to 2L. Which of the following statements is false? If you see in this figure, at the S it's a fixed, then there is a cantilever bracket PQRS where RS dimension is L and PQ dimension is L, and the length of QR is equal to 2L. There's a load downward force P applied at the point P with the value W, and we have to find which of the following statement is false out of all the 4 statements provided now. Okay, so let's see what are the options and let's work it around. So first statement is the portion RS has a constant twisting moment with a value of 2WL. Option statement 2 is the portion QR has a varying bending moment with a maximum value of WL. Option C is the portion PQ has a varying bending moment with a maximum value of WL, and option D is the portion PQ has a twisting moment of WL. Okay, rather than seeing all the 4 statements, let's see all the arms PQ, QR, RS, what is happening there. Let me draw it here. S is here, R, Q, P, and the W is downward. This is 2L. L here also L. In the PQ system, in the PQ arm, due to this WL, there would be a bending moment in this arm, and this would be a varying bending moment with the value at P equal to 0 and at the Q uh, for PQ it will be varying bending moment with uh, maximum value at Q and maximum value at Q, maximum value of WL at Q. Okay, now let's see QR at QR. So kind of now let what will happen is we have transferred this load to here. So the case of QR, we need to picturize. Now the load has been transferred to Q and there is a bending moment here. So for QR, it's a, so its value is W and bending moment value is WL. So for QR, this WL would be a kind of a twisting moment for that system, and it will be constant throughout. So for QR, varying bending moment would be there because of the vertical load acting downwards with maximum value of it would be 2WL at R and constant twisting moment of value WL. Now RS, for RS, now again picturize this load has been transferred here. There is a twisting moment here and there is W here, there is a twisting moment WL here, and there is a uh, moment generated due to this, and that value is equal to 2WL here. Now in RS it will be varying bending moment with maximum value at maximum value of WL at R, because as we move from R to S, there is an already a WL acting at R. So as we move towards S, this bending moment would be cancelled, would be reduced by the bending moment created due to this concentrated load, and at S it will be 0, and uh, and there's a constant twisting moment of value 2WL. Okay, so this covers, I think, all these things which are being created here. Let's see and work around what will be the correct answer and what uh, what will be the following out of all the four options, what all the statements are false. First statement is the portion RS has constant twisting moment with a value of 2WL. The portion RS has a constant twisting moment with a value of WL. So RS, yeah, is a constant twisting moment with a WL. So it's a correct statement. Yes. Now option B, the portion QR has a varying bending moment with a maximum value of WL. The portion QR is a varying bending moment with the maximum value is 2WL and it's here it's WL, so it's a false statement. Option C, the portion PQ has a varying bending moment with a maximum value of WL. So portion PQ is a varying bending moment with a maximum value of WL. So this is also a correct statement. Option D is the portion PQ has a twisting moment of WL. The portion PQ there is no twisting moment, so this is a false statement. Yeah, so so if you see option B and option D are the false statements. Okay, please go through this properly because it's a very good question and this would help you picturize what is happening exactly in the system. So how have I solved this? Is I just taken subsystem, the PQ, then QR and RS, and the meanwhile I've been transferring the loads and converting if there is moment or a bending moment or the twisting moment generated. You just transfer those things. Okay. Now moving on to the next question. Question number 9. The magnitude of the bending moment at the fixed end about axis 1 and axis 2 is. So if you see this question is say like it's same as in the previous question. So axis 1. So about axis 1, if I see uh, uh, the system, uh, the bending moment about the axis 1. So if you see the final thing RS, there is a varying bending moment with maximum value of WL at R. So at R it's WL, but as we move further, I'll just draw this thing. So in the last stage we saw it's value is W here and WL was here and 2WL was generated like this. Now cause this W uh, this bending moment WL would be decreased as we move further towards S from R to S, and at S that would be equal to at S uh, bending moment about axis 1 would be 0. So that is there. So because of the about axis 1, my bending moment will come out to be 0. We need to see about axis 2. So if you see uh, uh, acting load at P passes through the axis okay, leave this acting load W at P passes through the axis 2. Thus, uh, 0 bending moment will be generated about axis 2. Thus, our correct answer would be option C. Because in the case of axis 2, there is no lever arm. Even though there is a load, there is no lever arm. Thus, no bending moment would be generated about axis 2. Okay, moving on to the next question. Question number 10. A solid shaft can resist a bending moment of 10 kilonewton meter and a twisting moment of 6 kilonewton meter together. Then the torque which will produce the same shear stress when acting alone is. So this is what I have been telling earlier. This implies we need to just find the equivalent twisting moment or equivalent torque. So this is a straightforward question. We are given with the bending moment as 10 kilonewton meter, twisting moment as 6 kilonewton meter. According to the question, that we need to find the equivalent torque which will produce the same maximum shear, which is being produced by these two by the bending moment and the twisting moment provided in the system. That is equal to m square plus t square root of m square plus t square, and that is 10 square plus 6 square 100 plus 36 136, and so for sure it would be greater than 10. Let's confirm what would be the exact value. uh, 136 and 5, its value comes out to be 11.66. kilonewton meter. This correct answer is option B, 11.6 kilonewton meter. Moving on to the next question. Okay. Question number 11. A hollow steel shaft of 100 mm external dia and 50 mm internal diameter transmits 600 kilowatt at 500 rpm and is subjected to an axial thrust of 50 kilonewton. The bending moment that can be allowed safely to the shaft if the maximum principal stress does not exceed 120 megapascal. So in this question, there is an axial load already provided. There is an indirect way where the torque value has been provided. We are given with the maximum principal stress. We need to find the bending moment. Okay, let's write what all things have been given. So external diameter it's 100 mm, internal diameter is 50 mm. So it transmits power of, okay, so this time it's I'll just write this power as in this 600 kilowatt. Rotation with 500 rpm, rotation per minute. Axial load is 50 kilonewton. Sigma max it's equal to 120 megapascal. We need to find what is the bending moment that can be applied in this system. Okay, so first thing we need to find second write as n. So the first thing we need to find what is the torque applied in this system. So we are given with the power it's equal to 2 pi n. Just write this 2 pi n by 60 and times t, where t is my twisting moment. So power is 500 rotation per minute. I just converted those things. 2 pi this is 600. Okay, 600. 2 pi, the number of rotations is it's 500, 60 to t, and keep it in mind this is as of now in SI units. So to correct to write this 600 into 60, 2 pi into 500, this comes out to be 11.46. This is kilonewton meter. Okay, because this is in kilowatt. Kilowatt, right? Yeah. Thus, now I can write this as 11.46 into 10 power. Let's have written it correctly or not. Yeah. So 1.46 into 10 power 6 Newton millimeter. Now let's do the other calculations. Okay, so direct stress, axial stress, it would be equal to P by A, that is 50 into 10 power 3 pi by 4 D naught 100 square minus 50 square, and this comes out to be 50 into 4 into divided by pi divided by bracket 100 minus. This comes out to be 8.488 megapascal. Due to the bending moment, let it be as m. Sigma b would be equal to m by I into T naught by 2, and this would be equal to, I'll just write y as of now. So m I is pi by 64, 104 minus 50 to the power 4, y is 100 by 2. This equals to 50 into 64 divided by pi and divided by 100 to the power 4 minus 50 to the power 4. So this comes around 1.08649 into 10 power minus 5 m. Now due to the torsion, what will be my shear stress generated? It would be equal to T upon IP R, and that is 11.46 to 10 to the power 6 upon 5 by 32, 104 minus 54, 100 by 2, and this comes around 11.46 into 50 into divided by 5 divided by bracket 100 to the power 4 minus 50 to the power 4. This comes around 62.256 megapascal. Now the question is, maximum principal stress value is given as 120 megapascal. So I can say for sure sigma max is what? It will be equal to sigma A plus sigma B by 2 plus sigma A plus sigma B by 2 whole square plus tau square. And yeah, and this is equal to 120. A is 8.49. I'll just write this other one as of now as sigma b. (8.49) plus sigma b to whole square plus 62.256 whole square. So if I write this thing as sigma as of now, I can write 120 minus sigma whole square equal to sigma square plus 62.256 whole square. This would be equal to 120 square plus minus 240 sigma equal to 62.256 square. This will give me sigma value as, if I solve this, it will give me as 87.7 megapascal. Thus I can find sigma b as 87.7 into 2 minus 8.49, and that comes around 87.7 into 2 minus 8.49. This comes around 166.91 megapascal. Let's solve it further. There's 1.086497 into 10 power minus 5 m is equal to 166.91, and m comes out to be 1.086497, and comes around to be 15.36 into 10 power 6 Newton millimeter, or I can write 15.36 kilonewton meter. Let's see if I have done it correctly or not. Something mistake. Okay, there seems to be a mistake somewhere. Let me see. 62.256 square minus 120 divided by 240. Okay, so this comes around 43.85. So this would be equal to this would be 79.21 megapascal. 79.21 1.08 6497. So this comes around 7.29. So 7.29 kilonewton meter is the correct answer. and we can see option A matches well to this. Moving on to the next question now. Okay, so this question I would leave for the audience to solve. This would be a kind of a pretty good exercise. In this question also there's a question. In this question, uh, the diameter is provided, the bending moment and the twisting moment is provided. You just need to see the what is it like for what thing it should be designed, whether the maximum shear stresses or maximum normal stresses. So for this question you just need to find equivalent bending moment and then find the maximum shear stress and maximum normal stress and see which of it will match pretty well. Let's move on to this question, and hopefully this would be the last question for today's session. And after this, the questions which I will leave would be as a homework for you all. It would be a kind of a good exercise for you all, so you can work around it. Okay, let's solve this. So a question is, a shaft of 150 mm diameter is subjected to a bending moment of 3 kN meter and a torque of 4 kN meter. Considering Poisson's ratio as 0.3, the maximum direct stress induced on the section and the stress that upon acting alone can produce normal maximum strain respectively are. Okay, so there are two things: maximum direct stress and stresses that act upon can produce normal maximum strain. Uh, so quite a good question. Mm, mm, First thing, so diameter is given as 150 mm. Bending moment has 3 kilonewton meter, that is 3 into 10 power 6 newton millimeter. Torque value is given as 4 kilonewton meter, that is 4 into 10 power 6 newton millimeter. Poisson's ratio is given as 0.3. Maximum direct stress induced on the section stresses and the stress that upon acting alone can produce normal maximum strain respectively. Okay, so sigma max it's equal to okay 32 me by pi d cube, right? And that is 16 pi d cube m plus root m square plus d square. This is equal to 16 pi d cube. M is 3 plus, this is 3 square plus 4 square into 10 power 6. Okay, so if I write max upon min, this will be like this. Plus minus, this would be 5 10 power 6. Let's solve this. So sigma max 16 pi d is 150. So max is 8 into 10 power 6, and that is equal to 16 into 8 divided by pi divided by 150. Yeah. This is equal to 12.07 Newton per mm square, and minimum will come out to be 16 into pi 150 cube into 3 minus 5, that is minus 2 into 10 power 6. And it would be kind of divided by 4. So this would be minus 3.02 Newton per mm square. Now the first part, the direct stress induced on the section, maximum direct stress induced on the section, that is equal to this. Now the second part is stress, a stress that upon acting alone can produce normal maximum strain. So for that strain, to find that my strain would be sigma max by E minus mu by E, and this would be equal to sigma max is 12.07 by E minus, this would be 0.3, right? 0.3, and this is minus 3.02 on E. 0.3 into 3.02 plus 12.07. This comes around 12.976 upon E, and this implies the second part, whatever is being asked, it would be equal to this. Okay, this okay, so you can write this thing. This stress stress acting alone to produce the maximum strain would be 12.976 megapascal. So for the first part it's 12.07, and the megapascal or Newton per mm square. Okay, so 12.07 and 12.97. So correct answer is option C. Yeah. Okay. Now for the okay, so this is where I will stop now. I have written 3 more questions. You guys can work around, like this would be a kind of an homework for you all. Please go through this. This is similar to what we have already discussed. You just need to apply the same thing. For example, in this question, the load is applied at this point, so there is an eccentricity involved in this, so there would be a direct stress, axial stress, and there would be some of the bending stresses generated due to this, so there would be a positive and negative. Okay, and in this question, concrete column carries an axial load of this. So this is similar to what we have already gone through. In only the data is different, so you can easily work around this question. Okay, and for the last one, circular shaft is subjected to the combined action of bending, twisting, and direct axial loading. The maximum bending stress, maximum shearing stress, and uniform axial stress are produced. The maximum compressive stress produced in the shaft are. Okay, so for this, just combine all the try to find the principal stresses with the combination of the bending, twisting, and direct axial loading, and that will just solve this question. Should I solve this part? Okay, I'll just solve this one. So sigma b, it's sigma both tensile and compressive, shearing stress tau, it's root 3 sigma, both it can be both tensile and compressive, as in plus or minus I'm talking about. And axial stresses, it's a sigma, it's a compressive. Just don't write this sign here. There's sigma max would be equal to sigma a plus sigma b by 2 plus sigma a plus sigma b by 2 whole square plus 2 square. And this is compressive. If we join 2, this would be sigma plus 2 sigma by 2 sigma square plus root 3 sigma whole square. This would be sigma square 3 sigma square 3 3 2 sigma plus 2 sigma 3 sigma. So this is 8. So answer would be option C. And yeah, this is it. This wraps up today's discussion session. I hope nobody will have any doubt pertaining to this session. If you guys have any doubt, you are more than welcome to discuss about it. Use the discussion forum as much as possible. And yeah, so yes, this is pretty much what I wanted to discuss. Okay, see you in the next weekend, same time. Okay, bye. Take care. Have a nice day off. Thank you.